Please let me know if you can see the slide. Can you see the slide?
Yes,
Yes,
Miss.
Miss.
Okay, and please do let me know ASAP if the slides are not transitioning. Okay, I had a problem with other classes because it seems like I'm talking to myself, like not only one class, probably 3 classes. My slides are not moving, but I only came to know that it was not moving when there was a student who came in probably because he was disconnected or had a problem with connectivity and told me, Miss Ali, what are you talking? You're still on slide 1, but I'm already talking on slide 9. But nobody told me that that my slides are not moving. Anyway, class, my major frustrations actually. Anyway, so for this afternoon, we'll be talking about drying. And we'll be starting off with, of course, the fundamentals on drying, and that is regarding humidity, the water content of air that is primarily used for drying, and the water content of materials as well. So, but we'll start with of course, the very basic, which is the definition of drying. So when we speak of drying, it refers to the removal of relatively small amount of water from any material. So water is usually removed in the form of water vapor using air as the drying medium, or hot air blown over on top of the surface of the material to be dried. And this particular unit operation may also refer to the removal of other organic liquids, not only water. And these organic liquids here mentioned specifically are benzene. Now, is benzene rather. So usually it is the last step. This particular unit operation is the last step in a series of operations in a manufacturing process, which is usually carried out before packaging or dispatch. So I think it's very self-explanatory why substances or materials before packing them should have the appropriate moisture content. Otherwise, over time, the material will cake inside the packaging. So it should be within the allowable range of moisture content. Now, drying is carried out too. So these are the primary uses of drying: to reduce the cost of transport. So if there are excess moisture, there are added weight, and added weight means money or cost in transport. Also, to make a material more suitable for handling, as for example, with the case of soap powders or dye stuffs and even fertilizers. In the case of fertilizers, it's really very hazardous if these fertilizers are not in a dried condition wherein only sufficient amount of moisture is on it. So there will be, it will undergo chemical reaction later on if it has more than the usual moisture content that it contains.
Miss.
Yes, wala siya gamove.
Wala, Miss.
Oh my, sige, thank you. Then I'll use the unprojected slides. So we'll just enhance the size. I'm not sure what's wrong with my laptop now. So where was I? So we're here. I was explaining on drying being the usually the last step in the series of operations. That way, the material to be dried will only have enough moisture, or not more than the allowable amount of moisture that will prevent it from caking. Okay, so next slide was this. Drying is used to reduce the cost of transport, to make a material more suitable for handling, as for example with soap powder, dye stuffs, and fertilizers, to remove definite properties, rather to provide definite properties such as, for example, maintaining the free-flowing nature of powdered substances. This is again another self-explanatory thing. So if your substance contains more moisture than it should, it will not be as free-flowing as if it's in the condition where it has only enough moisture. Now, also it's used to remove moisture which may otherwise lead to corrosion. So one example is in the drying of gaseous fuels or benzene prior to its chlorination. Now, when we speak of moisture content, there could be two. So it could be the bound moisture or it could be the free moisture. So when we speak of bound moisture, this is water retained so that it exerts a vapor pressure less than that of free water at the same temperature. So such water may be retained in small capillaries or adsorbed on surfaces or as a solution in cell walls of living organisms. So these are bound moisture. Whereas free moisture, this is water which is in excess of the equilibrium moisture content. So anything that is in excess of the equilibrium moisture content, that is what we call free moisture. Now, in terms of the fundamental definitions of humidity and the different formulas associated with it, we're going to review on this. I'm sure you have, you had already your discussion of how to use the psychrometric chart then. And associated with that is the, of course, the principle or the concept of humidity. Now, in some reference books, this humidity is represented by capital letter Y. Now, in this set of slides, I'm using Colson again. So, humidity is represented as capital letter H with a specifying subscript to distinguish one particular type of formula from another. Okay? So humidity H is the mass of water per unit mass of dry air. So the water vapor content divided by the mass of dry air that contains such is your humidity. So in terms of partial pressure and total pressure, so your humidity is the partial pressure of the vapor in your water vapor air mixture divided by the difference of the total pressure minus the partial pressure of the vapor. Actually, this is the partial pressure due to your dry air, the denominator, because you're already subtracting the partial pressure of the vapor from the total pressure. Now, we have also humidity of saturated air, and this time it has a subscript of O. So it's capital H with the subscript of O, and this is the humidity of air when it is saturated with water vapor. So it contains the maximum amount of water vapor that it can contain in that particular specific condition. Now, in this particular condition, we can say then that the air is in equilibrium with the water at the given condition, of course, temperature and pressure. So in this particular condition, our humidity is H sub O when your air is already in the condition we call saturated condition. Now, as to percentage humidity, that would be the actual humidity over the humidity at saturation. So, humidity at saturation and actual humidity times 100. So, this one is lesser than the humidity at saturation. So, expect an answer here, which is, of course, less than 100. So, that's for your percent humidity. Now, percent relative humidity, on the other hand, is represented as R. Percent, oh sorry class, there's a typo here. Percent relative humidity is capital H with the subscript R. Okay? Now, for this, we have the partial pressure of water vapor in air divided by the vapor pressure of water at the same temperature. So partial pressure divided by vapor pressure, they are two different things. A partial pressure of water vapor and vapor pressure of water given the temperature at that condition. So that's your percent relative humidity, which is H sub R. Now we also have the concept of the humid volume. What's the humid volume? So this is the volume of the unit mass of dry air and its associated vapor, or simply the, shall I say, the inverse or the reciprocal of the density of your air and water mixture. So as you can see in the unit, it's cubic meter per kilogram. So the reciprocal of the density, but we're not talking of the density only of water, nor the density only of dry air, but the density of the air and water mixture. So as you can see in the formula, it's dependent on the absolute temperature and the humidity here, H. So the humidity, which is mass of water vapor over mass of dry air. Temperature, of course, has to be in Kelvin because the set units that you have here is in cubic meter per kilogram. So the volume of unit mass of dry air and its associated vapor. So and its associated vapor, meaning it's referring to the water vapor that your air contains. So mixture na nila na duwa. Now, we also have what we call saturated volume. So how is it different than the unit volume? So saturated volume is the volume of unit mass of dry air together with the water vapor required to saturate it. And as such, the term saturated volume. The volume of a unit mass of dry air, so meaning the set units is volume over mass. This case, the water vapor amount is the amount of water vapor that is required to saturate that given mass of dry air. So that is why it's saturated volume. Now, humid heat is somehow similar to the fundamental representation of the specific heat in thermodynamics of any substance. So specific heat, we also have in relation to the topic of psychrometry or drying, humid heat. And what is this humid heat? So it's the heat required, so in terms of the definition, comparable, good, to raise a unit mass of dry air again and its associated water vapor through 1 degree Kelvin at constant pressure. Now the formula, as you could see here, is 1 plus 1.88 H. So the formula for the CP, more or less the CP of your dry air and water vapor mixture is dependent on the humidity of such. So you could see that it's dependent on the humidity. With this formula, the set units is in kilojoule per kilogram Kelvin. Okay, so the set units that are given to you here are all in SI units. So if there's a need to convert to English, just use the appropriate conversion factors. Now we go to the dew point. Dew point. It is the temperature at which condensation will first occur when air is cooled. Okay, and then what about the wet bulb temperature? Now, if a stream of air is passed rapidly over a water surface, vaporization occurs, provided the temperature of the water is above the dew point of the air. The temperature of the water falls and the heat flows from the air to the water. So if the surface is sufficiently small for the condition of the air to change appreciably, and if the velocity is in excess of about 5 meters per second, referring to the velocity of a stream of air as it is being passed over this water surface, the water reaches what we call as the wet bulb temperature. And this is represented as theta with the subscript W, the wet bulb temperature at equilibrium. Now, this particular wet bulb temperature and dew point temperature are often discussed in detail in the topic of psychrometry. I think it was covered also in your thermodynamics or probably in your phychem. So just go over them again. So in this part of the slides, it's just being reviewed. Now let me see if it's working already. Can you see the slide? Time for drying.
Oh, miss.
Oh.
Definition of terms lang, miss.
Anyway, why gid siya? Hindi gid siya mag-project. So I don't know. Kaya I'm not comfortable with the transition of the slides. It's as if I'm just reading them if it's in this particular mode. Anyway, so we'll manage. So for time of drying, so for the time for drying, if a material is dried by passing hot air over a surface which is initially wet, the rate of drying curve in its simplest form is represented by this one, BCE. You have a constant rate period. In this constant rate period, you don't see any drop or decrease in the moisture content of your material that is being dried. And after the critical moisture content is reached, that's when the falling rate period occurs. So that's when the moisture content of the material starts to decrease. Now in here, I'm not saying, so I stand corrected, I'm not saying that there's no decrease in the moisture content, because from this part here to this part, there's already a decrease in the moisture content. But what I'm trying to say here, this is constant rate period because the rate in which the weight of the material changes over time and area per unit area of exposed surface during the drying time is constant. We have here on the vertical axis this rate, so that you could say it's rate because you have here the rate of change of the mass with respect to time, and you have here the area. This is the area of the surface that is being exposed to the hot air that is passing above it. So from W1 to WC, this particular rate is constant. And then from the condition we call the critical moisture content, if the critical moisture content is reached, that's when this particular rate is going to fall. So in this condition here, it's still constant rate of drying, that is, but moisture content is already decreasing because you can see here W1 to WC up to WE. As to what are these W1, WC, and WE, they are defined in here. So WE is the equilibrium moisture content. WC is the critical moisture content, critical in the sense that's when it's the time when the drop in the drying rate starts. Okay, so critical moisture content. And then we have W sub 1 as the initial moisture content. So we're talking of total moisture here. So total moisture content, initial total moisture content, critical, so total critical moisture content. All of these is in total moisture measurements, W1, WC, and WE. Now, if we intend to determine the time it would take for drying in the constant rate period, we label that particular time as T sub C. You have here the formula for such. So initial moisture content minus critical moisture content over the rate of drying per unit area, which is also equal to the product of the mass and the difference of the critical moisture content and the equilibrium moisture content. So if this R sub C is not given, you can express it in terms of this one, the product of the mass and the difference of the two moisture contents. Of course, A is the area of the exposed surface. So as you could see in this particular formula class, you need the W's, the moisture contents and the mass, together with the area of the exposed surface. For the falling rate period, you have now T sub F as the representation of the time for drying, and you have this one as the formula. You have W here as the total moisture content, or shall I say the moisture content at any time T. W is the moisture content at any time T, because anyway, all of these W's are total moisture content. And M is, as I mentioned a while ago, the mass of the material. If we want to determine the total drying time, then we need to get the sum of the two using the two formulas that you have here. So you determine the total drying time. Now, there are problems, class, especially hybridized problems on drying, wherein you'll be given tables. You'll be given particularly as a table that relates one particular property to another, and in which the moisture content are not simply stated as like this, like initial total moisture content, or shall I say equilibrium moisture content, or total moisture content at any time t. But rather, there are problems which would give a relationship between the free moisture content and another drying parameter probably. So it depends on the problem and how it's stated. So whenever such a particular situation arise, their free moisture content, the free moisture content should be expressed in this form, or should be accounted using this particular expression. The moisture content at any particular time, or at that particular time in which, say, the drying time is to be measured, minus the equilibrium moisture content. So the moisture content at any time minus the equilibrium moisture content is the free moisture content of your material at that particular condition, or at the given said condition by the problem. Okay? So we will now solve a sample problem, a simple sample problem based on the last three slides that we have covered, and how the formulas that they have been presented to you here should be used. Okay, so for sample problem number 1, you're given a wet solid which is to be dried from 25 to 10% moisture under constant drying condition in 15 kiloseconds, so equivalent to 4.17 hours. If the critical and the equilibrium moisture contents are 15 and 5% respectively, how long will it take to dry the solid from 30 to 80% moisture under the same condition? Now, you have to understand in this problem, class, that the time of 15 kiloseconds here that is given is the time it would take a material which has 25% moisture initially to dry to 10% moisture. So it would take it this much of time for it to dry. Now, the critical moisture content and the equilibrium moisture content are all, by the way, fixed values for a particular material for a set condition. So, but the problem here on the last part state that how long will it take for the dry solid, but this time it would have to start with a higher value of moisture, which is 30, and it will have to end to a much lesser moisture content of 8 compared to this one, the 10%. So more or less, you can expect that the value of time that you should be able to compute must much be higher. Why? Because you started off with a higher moisture content than 25, and you have to end with a much less moisture content than the 10, wherein you have this set condition here, wherein it took it 15 kiloseconds to dry. So we'll use our board again to show the solution of this particular problem. So let me share the board. Okay, wait, class, I can see. Okay, it's here. Okay. We'll write down the given information, the set of information that we can work out. So for an initial moisture content of 25, or that's 0.25, 25%, this is kilogram water per kilogram of material. So that already considers kilogram water and kilogram of the dry material. And we have here the final moisture content of 10%. So same set of units. Now we're given these fixed values of the critical moisture content, which is 15 kilograms water per kilogram material. And we have the equilibrium moisture content of 0.05. So this is how far the moisture content could decrease. Now, with this set condition class, it would take the material drying time of 15 kiloseconds. Okay, I will not anymore write the hour equivalent anyway, that could be easily converted. So we are required to determine the time for drying when we have to start with an initial moisture content of 30% and end with the final moisture content of 8%. Anyway, these are the information provided to us. We have 5 information, and from this we have to determine how long it would take for our material to dry, starting with 30% and end with 8%. So based on what we have discussed so far, so you have to think, we so far have only discussed the formula for the time for drying. And that would be the total drying time formula. And that's it. That's so far what we have done. So let's say in the first case, I'll place here case 1. I'll write the total drying time formula. So the total drying time, as shown to you a while ago in the slide, so it will take into account the drying time at constant rate period, and you have the drying time for the falling rate period. Okay, now we will, is there a mention about R sub C in the problem? The rate for drying. So based on what I have written here and based on the problem that was read a while ago, there was no mention of the rate of drying. So it's just appropriate that we will change the R sub C here to its equivalent expression. So we'll have this one. And I'll change the R sub C as to the product of M and the difference between critical moisture content and equilibrium moisture content. You have here A plus 1 over MA, still the same, ln of omega C minus omega E over omega C, or W. Okay, so it's actually italized W. Now you could see in the formula here that we have this common expression. So you have 1 over MA here and you have a 1 over MA here. So we can factor that 1 over MA. So I'll change my font so you see. And the rest that are not common, we'll copy again. So in here, for the first term, we're left with omega 1 minus omega C minus omega C minus omega E, or divided by omega C minus omega E. Now, in the second term, if we take out the 1 over MA, we'll have the ln of omega C minus omega E, omega minus omega E. I think it's forthcoming already what's to be determined here. Since there was no mention about the mass of the material, there's no mention about the area of the surface exposed to drying. So we'll have this determined based on the drying time that is already provided for the set condition that goes with it. So in this case, we will substitute the drying time, which is 15 kiloseconds, and I will substitute everything. So our initial moisture content is 0.25. I'm substituting to this formula class already, okay? That way we'll be left with MA. So I'll erase this part here and write MA. Okay, so you have 1 over MA here, and we'll substitute now values. So in this case, you will have 0.25 for the initial, 0.15 for the critical moisture content. And in the denominator, we have for the critical moisture content again, minus the final moisture content. Okay, then we have to add to this the ln of, so we have critical moisture content 15 minus the equilibrium moisture content, and then we have the final moisture content, which is 10%, and the equilibrium moisture content. So from in here, we'll get the value of 1 over MA. So your 1 over MA is equal to, if you substitute everything and simplify, I will just leave that to you. Your 1 over MA is 8.859. This 1 over MA, since we're talking of the same material, the same area to be dried, then this would be the 1 over MA that we will be using on our next set condition. In that next set condition, the only thing that will change is the initial and the final moisture content. Okay, so we'll have the T now for the condition we're in. We are to find the drying time. It would be 8.859. And this time I will use the new pair of values. So I have initial moisture content this time, which is 30. And here critical moisture content is still 15. And another 15 here. Critical moisture content and equilibrium moisture content of 5 plus the ln of, so we'll have critical moisture content, equilibrium moisture content. In here, that instead of 10%, it will end with 8%, and you'll have, again, your equilibrium moisture content here. So for the new set condition wherein we are to determine how long it would take to dry a 30% moisture content material to 8%, the answer is 23.95 kiloseconds. So notice I did not bother to place in here the units, because anyway, I will still be having that same unit later on when I solve for the new condition. So as mentioned a while ago, it's expected that we will have a longer drying time because we started with a much higher moisture content and ended up with a much less moisture content of 8%. So any question here? So this is our answer for this sample problem. Questions? So if there's none, okay, let's proceed. I'll go back to our slide. Okay, that's for our sample problem number 1. And we'll have our sample problem number 2. So I hope you can see it. Just let me know if it's not projecting properly. So in here, you're given a strip of material which is 10 mm thick, dried under constant drying condition from 28 to 13% moisture in 25 kiloseconds. By the way, class, before I read on, Don't misunderstand constant drying condition to constant rate of drying. When we speak of constant drying condition, the condition that is temperature and pressure. It's not to be misunderstood to be that you will only account for the time under the constant rate period. No, you're still going to account for the total drying time. That would be the sum of the time for the constant rate period and the falling rate period. Most of the problem always will say that any material is dried under constant drying condition, meaning the condition of the environment, the pressure, the temperature is fixed or constant all throughout the drying procedure. Okay, so let's continue. So if the equilibrium moisture content is 7%, what is the time taken to dry 60 planks from 22 to 10% moisture under the same conditions, assuming no loss from the edges. So meaning in this case, all drying will be on the exposed surface only, where the drying medium, in this case air, is passing through. All moistures are given on a wet basis. So meaning it's not per kilogram of dry material, but rather per kilogram of material with water. So the relationship between E, and what is this E? The ratio of the average free moisture content at time T to the initial free moisture content, and the parameter J is given by. So this is what I mentioned to you a while ago, that there are problems which will give you parameters relating the average free moisture content to the moisture content at any time, and final moisture content as well. So this is it. E is the ratio of the average free moisture content at any time T. So what is the free moisture content at any time T to the initial free moisture content? So with the parameter J. What is this parameter J? Because you're given here a set of data in the form of a table. Of course, expect that this J will be defined to you, or whatever parameter later on that the drying problem will talk about. So in this case, your J is equal to KT over L squared, where K is a constant. We can say that's the constant for drying, specific only for this particular material and for this particular set condition. T is the time in kiloseconds, and L is half the thickness of the sheet of material in millimeters. Whenever you're given such a condition as this, wherein the units in some way or another does not agree, like in this case, you have time in kiloseconds, but the thickness is in millimeters. So this is to be viewed as an empirical formula. A formula that was arrived based on, of course, the laboratory experiments that were conducted on this same material. So be very careful when such particular formulas are given, because whatever is the unit specified, you should conform with it. So if what you have is not, or what is given in the problem is not the units that are stipulated in the formula, there's a need, of course, for you to convert. Okay, so this is our sample problem number 2. It's asking for the time. Let me annotate. It's asking for the time it would take 60 planks from 22 to dry it from 22 to 10% moisture. Now, initially, these same planks, this type of planks were dried for a period of 25 kiloseconds. But look, the thickness is just 10 and the moisture content is higher at 28, then decreased to 13%. This one is lesser, 22, and decreased to a much lesser content. So same material but different, shall I say, characteristic. So in terms of geometric characteristics only, and the initial and final moisture contents for drying. Okay, so this is our set of information. So we now go to our word again for its solution. Okay, so this is our number 2. So we need to write the given first. So for number 2, the given, say case 1. What's case 1? You're given, remember class, I'd like to go to the problem. That thickness in this problem is not represented as T, but rather it's represented as L, because T in this case refers to the time for drying. So that is why the L that I wrote there in the given is not the length, but rather the thickness of the sheet of material. Okay, so I'll go back to the board. So your L here for case 1 is 10 mm. So this thick, initial moisture content of 28%. So I'd like to write 0.28. Final moisture content of 0.13. A drying time of 25 kiloseconds. You may wonder again why I say final moisture content. Moisture content at any time T could be final moisture content, as such because it's measured at any time during the course of drying. Then we have the equilibrium moisture content, which is 7%. Okay. Now, required, this is for case 2, when this time your length is 60 mm. Your initial moisture content is 22%, and your final moisture content is 10%. Okay? These are your information and of course the data in the table. Now, what do we do with the data in the table? In the first place, what do we do with it? Whenever you're given a table and you don't know what to do with it, then it depends on in the course of your solution. You can have it plotted to show the relationship of the variables that are related to each other, or you can first work out on the information that is provided in the problem, then try to think of how you're going to use the set of data that is provided. Now, there was a mention in the problem about the E. I'd like to go back to the problem. Is this mention here about the E? And you see that E in here. Okay, 1, 2, 3, 4, 5, 6, 7 pairs of information relating E to J. So you have E, which is the free moisture content at any time T and the initial free moisture content. Now, it's going to translate that into an equation that we can work out. So the ratio of the initial moisture of the moisture content at any time T, so ratio meaning you have a fraction to the initial free moisture content. Now, a while ago, we mentioned about the free moisture content as the difference between the moisture content at any particular time with the equilibrium moisture content. So you can apply it here. So you have moisture content at any time minus, or the final moisture content minus the equilibrium moisture content over the initial moisture content minus the equilibrium moisture content. This is free moisture. This is also free moisture. But this one is free moisture content at any time T, or final free moisture content, and this one is initial free moisture content. So this is the E that you are seeing in the table, in the worded problem that was shown to you a while ago. So in our initial condition, so for case 1, So if you intend to determine for case 1, then we'll place here E sub 1. Then I'll place in there the value. So you have your initial moisture content of 0.28. Your equilibrium moisture content is 0.07. Your final moisture content of 0.13. And still here, the equilibrium moisture content. This will give you an E value which is equal to 0.286. Okay, kindly check. Now, this is your ratio for the final free moisture content to the initial free moisture content at the condition that this is at a drying time, a total drying time of 25 kiloseconds. Now, what are we going to do with this? Remember that this E is being connected to the J in the problem. Go back to the problem here. This E is being associated or connected to the J. And look at the J in terms of its formula. The J has the time for drying. It has the constant K. And it has the thickness of the material. So meaning this J will vary depending on the time of drying and the thickness of the material, as you could see in here. But we can say that since this K is a constant, it's a property of the material, the plank that we're talking about in this problem, this K will be true, will be the same whether we're talking of this thickness of material, which is 10 mm, or whether we're talking about this material, which is 60 mm. So then having said that we will associate, or we will use the J formula here together with the time and the thickness in the first case. How are we to treat this information that you have here tabulated? So this particular problem is actually solved both analytical and graphical. So you can graph, I'll show to you the graph of E versus J. I'll just label this one. So this is your E here, and this is your J. It's not a smooth curve because I just used the Excel curve to have it plotted. So it's not the best fit curve, but it's just per se the curve when all the points are passed through. But this is our curve for the set of information or in the table that you have seen here in the previous slide. So what are we going to do? So remember, go back to our board. You already determined the E for the initial case, and that's our case 1, and that's 0.286. So you can use that E to find the K because we're talking of the same K for the same material. So I'll show to go back to this one. What you could do is find the 0.286. You find the 0.286 in this graph. You have here 0.1, you have 0.2, you have 0.3. So this is 0.5, this is 0.75, probably in here. And probably if I will project this point here to the right, 0.5, 0.75, 0.8, 0.5, 0.75, 0.8. Somewhere here. I'll go here. Very rough though. So more or less, this is the point where E is more or less 0.286. So what will you do with that? With this E, which is 0.286, you go down and you find here the J. This J, which is K T over L squared. Okay, what is this J? So from this graph, more or less, you can say that if this is 0.6, this is 0.55, this is 0.25, probably this is 0.52. So I can say that this J here is more or less 0.52. So how am I going to make use of this information? I'll go to our board. Okay, and use 0.52 for the J. So from the graph, your J is more or less 0.52. Close this one. So if it's 0.52, then we'll have J equal to K T over L squared. And this is equal to 0.52. And this is equated to K. Your drying time in this case is 25. And we divide by half the thickness of the material in mm. So half the thickness of the material in mm is 10. That's our thickness of our material divided by 2. And we square it. From in here, we can get the value of the constant K, which we can use for the new condition. Your K here is also more or less equal to 0.52 if we're using a J, which is 0.52. Now, this is for case 1. So if you go to case 2, so using case 2, condition, then you can have, again, the E. We first have the E. So we'll have the ratio of the final free moisture content to the initial free moisture content. So this time our final moisture is 0.20, initial rather. Wait, 0.22 is our final moisture content. You have equilibrium moisture content of 0.07 and an initial moisture content. I think I got it switched. Let's go back to our problem. So initial is 22, final is 10. Okay, so we'll go back to our board. So this should be 10. This is really initial. So that is why I was pausing because it's too big. So this is for the final, and for the initial is 0.22. And you have here also 0.07. So with this, your E is 0.2. What would you do with this E, which is 0.2? Go back to your graph. Annotate. Your E, which is 0.2, is this one. You go here and you'll end up here. And you'll have more or less this part, the J, which is equal to 0.6, 0.7, 0.75, 0.625, 0.626, 0.5, 0.625, 0.6 something, 0.6125. Okay, so if it's 0.6125 here, so it depends on your reading actually. Cross 0.6125. We go to our board and put here a J2, which is 0.6125. Okay, here our J1 is 0.52. So we have this one as 0.6125. So with this J, you can find the drying time for that new thickness of blank starting with a different moisture content and ending with a different final moisture content. So we'll have 0.6125 equal to KT over L squared. And we will substitute the K that we got from the first case here, 0.52. We have the drying time here for case 2, and we have the thickness of the plank. So this time our plank is 60 mm thick. So we'll divide it by 2. So 60 divided by 2 squared. So you will have your new drying time for the new condition for case 2, that is. So your 0.6125, we multiply 230 squared and we divide by 0.52. That should give us 1060.10 kiloseconds. So if you divide that by 3,600 kilo hours divided by 1,000, that's hours divided by 24. In terms of days, that would be 1060.10. So that's seconds. We divide by 3,600 seconds. And divided by 24. This is very long. So 12.27 days. It would take 12.27 days for your 60 mm thick plank, starting with a moisture content of 22 to dry to 10% moisture. So this is the answer to our problem. Okay, any questions? Any question? Okay, so that's it in terms of the application of the set formula, the first, I think, 3 formulas that were shown to you. Now, in this next slide, I've placed here that you have additional readings in McCabe and Jean Couplis on drying. So please read the sample problems in these 2 books as well on drying. So mostly, class, the problems that you see there are material balance, application only of material balance. Okay, we go to this particular 3rd sample problem. Are you there?
Yes, Miss.
Okay. Sige. So we're given a granular material containing 40% moisture and is fed to a countercurrent rotary dryer at a temperature of 295 Kelvin and is withdrawn at 305 Kelvin containing 5% moisture. Now the air supplied, which contains 0.006 kilogram water vapor per kilogram dry air. So this refers already to the humidity of air, enters at 385 Kelvin and lives at 310 Kelvin. The dryer handles 0.125 kilogram per second of wet stock. So this is the feed rate to our dryer. Assuming that radiation losses amounts to 20 kilojoule per kilogram dry air used, determine the mass flow rate of dry air supplied to the dryer. So this is the first requirement, the mass flow rate of dry air and the humidity of the exit air. So since we're using air which is not, shall I say, totally free of water vapor, and this particular air will also carry with it the evaporated water from our wet stock, then we expect that the humidity of our exit air will be higher than its initial humidity. So we are to determine what is this exit humidity of our drying medium, which is air. Now you're given here the latent heat of water vapor at 295 Kelvin, which is 2,449 kilojoule per kilogram. So take note that this latent heat of water vapor is not based on 100 degrees Celsius, but only at 295 Kelvin. Now, specific heat capacity of dried material, our feed, which if dry has a specific heat of 0.88 kilojoule per kilogram Kelvin, and our air, the specific heat capacity of dry air in particular is 1 kilojoule per kilogram Kelvin, and the specific heat of water vapor, so notice that it's separate, specific heat of dry air and specific heat of water vapor to be 2.01 kilojoule per kilogram dry air. So in this case, we are to determine this. The mass flow rate of dry air that is supplied to your dryer and the humidity of the exit air. So two things based on the set condition. And notice as well, class, that I haven't given you any other formula. I did not give you any additional formula except for the drying time that I have discussed a while ago and the formula regarding the free moisture content. That's all that I gave you. And let's say you're given this particular problem. It does not involve any design. You don't design your dryer in this case. All you have to do is determine the amount of dry air that you will be using in enough amount to dry your material to the specified condition and the humidity of that particular dry air. So this will tell you, class, that or this particular problem then will simply apply previously learned principle on heat transfer, energy balance, mass balance, and everything in between that you have learned already. No additional info for now as to design because we're not designing. So then, having said that, you should be thinking that what probably I'm going to use here is just pure material and energy balance together with what I've learned in thermodynamics. Okay, now we'll go to our board for the solution of this third sample problem. Okay, I can't see my board. Okay, let me share. Okay, so problem number 3. Start with the given. Let's say we'll just have a very simple representation of our dryer, a box. In this dryer, you have your feed, and the feed is given at this flow rate, 0.125 kilogram per second. So this feed is wet. Now it has a moisture content of 0.40 and temperature and a temperature of 295. So this is stated in the problem. Now it is to be dried to this condition. So final moisture content of 5%. And I'd like to have this as 1. And this is the final temperature of our dried feed, 305 Kelvin. Okay. Now, in this dryer, going to use air. And for this air, the initial temperature is 385 Kelvin. The final temperature is 310. Now, there is going to be water evaporated, but this is no separate water because water vapor, this water evaporated is in a form of a gas, water vapor, and it's carried with your exit air here. But nonetheless, just for illustration purposes, to see what comes in and out of our dryer, this is the amount of water vapor V. Okay, our air here has an initial humidity. So I'd like to label that as H sub 1 of 0.006 kilogram water per kilogram dry air. I'd just like to abbreviate dry air as DA. Now, based on what the problem requires, it's asking for the mass of dry air. Now, if you're going to look into other books on drying other than the one in John Pupley's and even in McCabe, mass of dry air class is represented as G. Okay? This is the mass of dry air, which we do not know. And then we are to determine as well its exit humidity. So these two, we have to determine. So in terms of our required information, we need the G and we need to know the H sub 2. So this G is the mass of dry air without the water vapor that goes inside your dryer to dry your wet stuff, your feed. Okay? Now, what else is given? So there are a lot of given in terms of the CPs. I'd like to write it here one by one. So the CP of the solid, I'd like to refer to the dry material to be the solid. That would be 0.88 kilojoule per kilogram Kelvin. The CP of dry air. So it has its own CP, which is 1.00 kilojoule per kilogram Kelvin. We have the CP of water vapor. Place it here. That would be 2.01 kilojoule per kilogram Kelvin. What else? So these are the three CPs mentioned. And we have the latent heat of vaporization at 295 at this temperature. So I'd like to write it here na lang. There's no space. This is at 295 K. And that's 2449 kilojoule per kilogram. And then what else? Radiation loss. Or since we'll be using Q here for heat, Q due to radiation, and it's loss, so it's negative 20 kilojoule per kilogram dry air. So that's how important is the mass of dry air, because even the radiation loss is expressed based on this amount that your dryer used. Okay? Let me see. I think we're good to go. So these are our information. I mentioned a while ago that you will use here material balance with energy balance coupled with your thermodynamics. So we'll proceed with our solution. So if you're going to do material balance coupled with energy balance, the main thing that we are to start off in here, that way we can account for the mass of dry air, is of course energy balance. We need to account for the mass of for that energy that enters the dryer, the total amount of energy that enters the dryer, and the total amount of energy that leaves the dryer based on the streams that comes in and out on it. Now, we need to have a basis temperature though in determining these particular energies. So we will use a basis here. So since we're dealing with SI unit, we're using a basis datum temperature of 273 Kelvin. Okay, 273 Kelvin. So we will start with the amount or the Q that enters our dryer, the total energy that is entering our dryer. So we will label our streams in this case properly. That way we can account for this particular energy. So going back to our given, so we have here actually 5 streams. So we will have each of the streams labeled. Okay, so we have our feed. So we will start with our, let's say we'll start with the drying medium wherein we want to determine the G. So let's label this stream as 1. So it's entering the dryer, and this stream as 2, another stream that is entering the dryer. Then the living streams, we have the dried feed, and then the wet air, and then the vapor evaporated from the wet feed to lower down is moisture content. So let's say that's how we're going to label our stream. So let's now start with our energy balance here. So based on our labeling here, anyway, I've mentioned it a while ago, if we need to account for the total energies entering our dryer, that would be for this stream and for this stream. So your Q in must be equal to Q1 plus Q3. Let's check. Okay, it's 2. So this is Q2, and this is our first equation. Okay, we need to determine what is Q1 and what is Q2 and go back to it after. So Q1. So we're talking about the energy content of the air that enters the dryer. So that air is composed of course dry air and the water vapor that it contains, because there's no such thing as a 100% dry air. So in that case, you go back to what you've learned in your thermodynamics in terms of accounting for the energy contents of substances or materials. So we go back to the formula mCp delta T. Okay, the first one is for dry air, and mCp delta T. This is for the water vapor. Okay, we'll just abbreviate it as water vapor or simply water. For your dry air, the mass based on our given here, we do not know it. We set it as G. So we multiply, we start writing here G. And what is the Cp of dry air? We wrote it here a while ago. So this is the Cp of dry air. So I'll place here 1. And the delta T. So our dry air class is at a temperature of, based on the given, 385. So you will have your 385, and you will use its difference with the datum temperature, which is 273. So this is for our dry air. Now we go to the water vapor. Now, the mass of the water vapor in our heating medium that enters here, how do you get it? The mass of the water vapor based on the information that you are seeing here. Anybody? How will you get the mass of the water vapor alone? That would be what? That would be, of course, the humidity. You have the humidity, that's water vapor per unit mass of dry air, and you multiply it with dry air. This whole thing is the mass of your water vapor. Okay? The Cp of your water vapor, what is the Cp of the water vapor? 2.01. And what's the delta T for this water vapor? That would be the same as this one because they are at the same temperature. So you have 385 minus 273. So in here for Q1, please check my answer. For Q1, you will have 113.35 G. I have my unknown here, G. My unit here is kilowatt, kilojoule per second. Okay, that's for my Q1. I'm done with Q1. Now I can go to Q2. Remember, this Q1 is for my air entering the dryer, and Q2 now will be my feed. Okay, any questions so far here? You accounted for the energy content of the dry air and added to it the energy content of the water vapor that goes with it, based on its humidity. Okay, none. So we go to Q sub 2. So Q sub 2 has something to do with the feed. So in terms of the feed, our feed has the MCP delta T of the dry solids or the solids plus MCP delta T of water. So it's not water vapor, but it's really water that goes with your wet stock. Now we substitute. So for the solid, what would be the mass of your solid alone? So look at here on the given. So this is 40%. What is this? Moisture. Then the other must be your dry solid. So what would you do? Here you will have your feedstock 100 or 0.125 kilograms per second. You multiply it with 0.6 because your moisture content is 40%. And then you multiply it with the Cp of the dry solid. What's the Cp of the dry solid? 0.88. So I have here 0.88. And the temperature of the feed, 295. So you have here 295 minus 273. Okay, this is for our solid. Now we go to our water in the feed. It's the same thing, 0.125, the rate of our feed, but this time it's 0.4. The water content, water in the feed is just 4.18, the Cp of water, and your temperature is still 295 minus 273. Now you will have here a Q sub 2, which is 6.05, also having a unit of kilowatt. Now, if you substitute Q1 and Q2 to 1, did I place equation 1? Yes, to 1. So this will be Q in. So your Q in will be 113.35 G plus 6.05. The unit of this is in kilowatt. You still have the unit G here. Not the unit, but the unknown G rather. This we will label as equation 2. Any question? None? Sige. So we go to the energies leaving the dryer. So now we're going to account for Q out based on our given our illustration. Q out. You have four. You have 3, 4, 5. Okay, 3, 4, 5. So I'll place here 3, 4, 5. Equation 3. So I'll start with Q3. The first thing that I'll have here is Q3. So Q3 is the, look, energy of the dried feed. So your dried feed, of course it still has water on it, will be having what? The MCP delta T as well of the dry solids plus MCP delta T of, I'd like to place here remaining water. Why can't I just simply write there water? Because remember, a portion of the water that is initially present in your feed is evaporated. That way, it's going to dry up. Its moisture content is going to reduce. So meaning this MCP delta T here on the second term will be for the remaining water. Now, let's check. So if it's the CP of the remaining water, then I can do my usual thing in the previous equations wherein I just simply substitute MCP delta T because I do not know the amount of this remaining water. The only way I can determine this amount of remaining water is for me to first determine this particular amount based on this given here. So let's go back on the given. You have this one? 0.005. So we will use this particular 0.005 to determine the mass of the remaining water. How do we do that? Anybody? How do we determine the mass of the remaining water? Based on the 5% moisture. I label this as equation 4 because I can't directly substitute now. What do we do? Okay, I'll write here 0.05. What is this moisture content? Isn't this, I'd like to place here remaining water. I label this RW. Remaining water, what's the denominator? Come on, so you will not be bored there. If it's 0.05 here and I place remaining water here, what should be placed in here? Remaining water plus solid, right? Remaining water over remaining water plus solid is the percentage of water living with your processed or dried feed from the dryer. So I'll get now the remaining water. Okay, so you have 0.05. I have remaining water. Remaining water. What is this solid? We know it. It's supposed to be the only thing that will remain unchanged in this entire process. The dry solid and the dry air. So you'll have 0.125. This is the rate of our feed. We will multiply it with 0.6 because our feed is 40% moisture. So meaning 60% of that is dry. That 60% part dry of 60% part of your feed that is dry is your solid. So you have this one. So I'll get the remaining water or the living water. Please check my value. It's 0.00395. You get it? Any questions so far? I'll proceed. Then can we go back here? Now we can go to Q3. From 4, Q3 is equal to, okay, this is for the solid. What's our solid? We go back again. Mass of the solid is the rate of the feed times 0.60. That's it. That's its mass. Then the CP of the dry solid. What's the CP of the dry solid? 0.88. Now, since my temperature here for both will be the same, I'll just anyway, sige na lang. Base psychrometry siya mo. So we started with a 295, I think, feed. And it leaves the dryer at this temperature, 305. So 305 minus 273, because this is our datum temperature plus. So we determined already the remaining water here, 0.00395 times 4.18 times 305 minus 273. So this is what I meant, class, that you can just have this added and then multiply the sum of the two rather, by the difference of these two temperatures, because we're still using the same difference temperature. So in here, you'll have 2.59. Still having the unit of kilowatt. Okay, we're done with Q3. We go to Q4. What's Q4? The living air, the exiting air from the dryer. So then it will have MCP delta T, again dry air, plus MCP delta T, water vapor. Okay, that's for our Q4. What is our dry air? So our dry air has a mass of, we do not know, this is G. A CP of, what's the CP of our dry air? 1. So this is 1. This time your temperature is lowered to 310. So we'll place here 310 minus 273. Right? Now we go to the water vapor. What about the water vapor? So you will have 0.006 again times the G, humidity of the entering air times the mass of dry air, that would give you the water vapor. Its CP, which is 2. I might get it wrong. Water vapor, 2.01. You have 2.01 and you have a temperature of 310 minus 273. So you can have this factored and just get the sum of these two. So from in here, your Q4 will be in terms of G. This has a G in here and another G in here. So you'll have here 37.45 G. So this is in kilowatt as well. So last stream, that would be the water evaporated. But again, it's not a separate stream, class. I just presented it here as a separate stream, so you'll be able to account for it. But actually, this water evaporated goes with your air here that leaves the dryer. but we will just account its energy separately. Okay, Q5. Okay, the energy content of your evaporated water. If I will ask you, how much is the evaporated water? How will you account for the evaporated water? Because anyway, that would be mCp delta T for this particular evaporated water. But how much is this evaporated water? If it's mCp delta T, you still need the M. If this Cp delta T will account for the sensible heat, the latent heat, and another sensible heat for your liquid water to be turned to water vapor, you still need this M. So I'm just asking, how will you find the amount of water evaporated? Based on what we have discussed, how will you find the amount of water evaporated? Material balance, a simple material balance here. So you will have a guide. How will you determine the amount of water evaporated? Anyone? Water evaporated. Oh, miski matulok lang kamo dao sa aton illustration. You will see where will water, where are we going to base it? Water evaporated is what? Based on your illustration, how will you account for water evaporated? Material balance lang. Hindi magpanumdum, sang tayo. Water evaporated is? Okay, this M water in the feed minus water remaining in the dried feed, right? Why? Your this M here, the M that we're going to place in here is 0.125 times 0.4. This is the initial water content minus the amount that we already determined a while ago, the remaining water based on the final moisture content of the dried wet stock. And that's 0.00395. So what happened to this? .00395. So your mass here for Q will be our mass for the water evaporated. 0.0461. 0.0461. Do you follow this? Simple. How much water has evaporated? Di man siya makadto. Pag nag-evaporate siya, kay ti amoni ang iya initial water content. Amoni nabilin. So the rest evaporated or went with your air, your heating medium, which is air. So it's 0.0461. Now we go to Q5. We go back to Q5. So Q5 is equal to 0.0461. It would have been, class, a very simple case of sensible heat, the usual formula that we're using here. We've been using it here repeatedly, but this time it would be different. Because I mentioned a while ago, I mentioned that the water vapor that is taken from the feed to dry it up or to reduce its moisture content actually went together with your heating medium, which is your air. So if it has to go together, leave your dryer together with your heating medium air, then the original water, which is liquid, has to be turned into vapor. So it has to have sensible heat. You've learned this already since chemistry. If there has to be a change of phase, there has to be sensible heat, there has to be latent heat, and another sensible heat if there's a need to be for another sensible heat for in that case. If your latent heat temperature is different than the indicated temperature at the end of your, let's say, heating process or cooling process or in your change of phase. So in this case, we will modify the CP delta T that we have here, but we will add two more terms. So the first thing that we're going to account for is the sensible heat for that particular liquid water to raise its temperature to 295 from the datum temperature, which is 273, because we've been using the datum temperature, which is 273. In that case, if it's still liquid, in that state, we will have 4.18 and we will have 295 minus 273. This is your sensible heat here, based on the datum temperature to reach this particular temperature. If you recall, a while ago, upon reading the problem, the provided latent heat is at 295, meaning at that particular temperature, water will turn into a vapor. So there's going to be a change of phase. So the lambda that is provided is at 295 Kelvin and it's at this value. So we're going to add here the latent heat. So we have here 2449. However, so this, it has already changed phase, but your water that is already vapor at this stage here is at only 295. The air leaves the dryer at 310. Here. So your water vapor, which goes with it, this air should be at this temperature as well. So you need to add another sensible heat here. So plus, so in this case, you will have now water vapor, the CP of that is 2.01, and you will have here 310 minus 295. Because this latent heat is at 295, so you need to increase its temperature to 310. This is now the total energy content of the water that was vaporized that went together with the air as it leaves the dryer. So your Q5, if you're going to add all this up, is 118.27 kilowatt. Okay? And you have everything already. You have Q in equals to Q out plus, don't forget, radiation loss. So there's loss, radiation loss, so it has to be with Q out. So we have now energy balance. Q in equal to Q out plus Q radiation. Okay? But your Q out is this. So all you have to add all of this. So from equation 3, this is already equation 4. So this must be equation 5. So from 3, we need to add everything. So Q out is equal to 345. 2.59. 137.45 G and 518.27. This is your Q out. Can you please add? I did not add it. You only need to add 2.59 and 118.27. So you have 120.86 plus 37.45 G, and you equate Q into this value and radiation loss. So your Q in 113.35 plus 6.05. From 5, 113.35 G plus 6.05 is equal to 120.86 plus 37.45 G plus 20. Radiation loss is 20, but be very careful the way it's stated. Radiation loss is 20 per kilogram dry air. So that one needs to be multiplied by G. So not multiplying it by G will make your solution wrong because this is per kilogram of dry air. So you'll be able to solve here for the first requirement, which is G. Okay, can you solve for G? Uh, 120.86 minus 6.05 divided by 3.35 minus 37.45 minus 20. Okay, my G, 2.054. Correct. 2.054. So this is kilogram dry air. This is our first unknown. Next, humidity. How will you determine humidity? Okay. Material balance again. How will you determine the humidity of the exit air? It should contain the water that it initially has. It should contain the water that was evaporated. So how would it be? That would be, I already guided you. It should contain the water that it originally has. So its initial humidity, that's its initial humidity. You have to multiply it with that because this is per kilogram dry air. That way it will be water vapor plus the water vapor coming from the wet stack, 0.046. We divide by the, of course, the G, which is 2.054. This is the humidity of your exit air. Oh, so humidity is 0.0284 kilogram water vapor per kilogram dry air. This is the answer to our problem. Okay, so that's it, class. You did not learn anything new. You simply used energy balance and material balance in the case of this particular problem. But you use previously learned principles. You use the principle of the formula of MCP delta T, and this one, very important. When a substance change phase, you have to account for all the energies associated with it. So you have to consider the latent heats and the sensible heats. Okay? My time is 6:35. I'm sure it's already info overload for you today, for majority of you, if not for everybody. Do you have any questions?